Two bodies are thrown with the same initial velocity at angles alpha and 90 degree minus alpha with the horizontal. What will be the ratio of maximum heights attained by them? So it's the projectile motion case, two bodies. Let me draw a quick diagram at here. So this is x and y plane. A projectile is projected with two angles. Now it is projected with an angle alpha with the horizontal. So if I take this is alpha and another angle, this is nothing but goes to 90 degree minus alpha. So it is making an angle with the horizontal. Okay, it means I need to pull it all the way down. I hope you have clear cut it here. Yeah, one is alpha and another one is 90 degree minus alpha. Now here we need to find that the ratio of maximum heights attained by them. A simple case. Now if theta equal to alpha, the maximum height, what is the maximum height formula you get? Maximum height h equal to u square sine square theta upon 2g. So this is the formula for maximum height, and in this case the value theta changed to alpha. So if I can call this as maximum height for alpha, don't get confused, otherwise I can use a symbol as h1, because this is case 1. I can take if theta equal to alpha. Now it's okay. h1 equal to, I can add that to u square and sine square in the place of theta. I need to put alpha upon 2g. That is case 1. When it comes to case 2, if theta equal to 90 degree minus alpha, then maximum height, in this case I would like to take as h2 equal to u square sine square 90 degree minus alpha upon 2g. Yeah, here again I use trigonometric formula, sine 90 degree minus theta equal to cos theta. Now if I use right at here h2 equal to u square, so this converts as cos square alpha upon 2g. So this is equation 2. We need to find ratio. It means we need to divide 1 upon 2 to get ratios. So h1 upon h2 equal to u square sine square alpha upon 2g upon u square cos square alpha upon 2g. Now you cut u square and 2g and 2g. So the ratios h1 upon h2 equal to sine square alpha upon cos square alpha, which is equal to tan square alpha. But we need to write as ratios, so it's only single term. So we can write upon 1 and it will turn as tan square alpha is to 1. So that is the height ratios if the angles are alpha and 90 degree minus alpha. All you need to do that, remember the right formula for maximum height. So the height ratios are tan square alpha is to 1. Let's try one more problem. At which point on the projectile trajectory is the potential energy is maximum and the kinetic energy is minimum and total energy is maximum. Understand the question carefully. At which points on the projectile trajectory? So we need to specify in the projectile trajectory at which points. At which points potential energy is maximum and kinetic energy is minimum and total energy. What happens to total energy? I hope you know the potential energy formula. It goes to mgh and kinetic energy equal to half mv square and total energy equal to sum of the kinetic energy plus potential energy. Now we need to specify and show in the projectile motion and where are these points. Suppose if I take this projectile motion x and y plane, so if a projectile is projected with an angle theta with the horizontal, where is the potential energy is maximum? You think in common sense? So in this formula, mass of the object and acceleration due to gravity, these two terms is constant. So the variable term here equal to mgh. So we know that in the projectile motion, the maximum height, so the location of the maximum height, suppose if you take this is h max, height max, so at here at maximum height the potential energy is maximum. So that I can mention at here for the first case, potential energy of a projectile is maximum at its highest point. At its highest point. Reason? Because height is maximum. Because height is maximum. Therefore, if we can do some little math that here, potential energy max equal to mgh. I can use capital H at here, no need, because you don't worry about that, because all the way I am using capital H for the height maximum. Now remember the formula for the H max, height maximum. So mg, the maximum height formula goes to u square sin square theta upon 2g. U square sin square theta upon 2g. Now potential energy maximum equal to, let's try eliminate which are the terms will be go away. Now we can end up this as half 1 by 2 m u square sin square theta. So this is the expression what I got for the potential energy maximum of m u square sin square theta. So when it comes to kinetic energy minimum, the kinetic energy minimum, to discuss that, look into the formula. Kinetic energy formula equal to half mv square. So I need to find in the projectile motion where the velocity is less. Then only I can get the kinetic energy is minimum, because its formula goes to half mv square. So where the projectile motion velocity is less, if you remember that, so projectile is having two velocities. Horizontal velocity remains constant. You can change the color. Horizontal velocity and vertical velocity. So this vertical velocity component is keep on decreases. At highest point we have only horizontal velocity. There is no vertical velocity at here. And soon after that again the velocity is increases. velocity of vertical component is increases, horizontal velocity remains constant throughout the projectile motion. At the end also, the velocity, what the velocity is starting, so the same velocity will be at the end. But when it comes to at highest point is something special happens. The vertical component of velocity will become 0, only horizontal component of velocity constant. So in that particular case, the velocity is minimum. So that is something different, something unique, peculiar in the projectile motion. For the second case, kinetic energy, first I will mention velocity, then we can apply kinetic energy. Velocity of a projectile is minimum at highest point. Reason, vertical component of velocity equal to 0. Now in that case, I can write it here. Kinetic energy of projectile is minimum. It's minimum, it's not 0. Velocity is not 0 anywhere during the total projectile motion. It's just minimum, but it's not 0 at its highest point. At its highest point, because it's minimum velocity. Now we need to mention kinetic energy formula. So the kinetic energy at highest point, equal to half mv square, velocity at highest point. So this velocity is also horizontal velocity. Yeah, h is matching on both cases. At highest point it's having only horizontal velocity. The horizontal velocity, we can take that half m times horizontal velocity equal to u cos theta whole square. That is the horizontal velocity if u is the initial velocity. Now this you can simplify. It's very easy. Half m u square cos square theta. So this is kinetic energy at highest point, not horizontal. Kinetic energy at highest point. So this I will take as equation 2. I will make use to solve the third case. For the third case, we need to find the total energy. Total energy at highest point. So total energy at highest point equal to potential energy at highest point plus kinetic energy at highest point. And we got the two equations at here. Just combine equation 1 and equation 2. So potential energy at highest point is equal to half m u square, that is sine square theta, and kinetic energy at highest point half m u square cos square theta. So half m u square you can take out common, became sine square theta plus cos square theta. Now this I mentioned that half m u square of 1 equal to half m u square. So total energy at highest point equal to half m u square. So not only this is the energy at highest point, so this is the total energy at the point of projection. This is not only the energy of the projectile at highest point. So this is the only energy which the projectile is having at the initial point. So that is also an important point at here. So this is the total energy at the point of projection. So at the point of projection, it means at the starting point. At the starting point, what is the energy just after launching? What is the energy of the projectile which it is having? It is just half mu square. Here u is the horizontal velocity. The same energy remains constant throughout the projectile motion. If energy remains constant throughout the projectile motion, that we say it's conservation of energy. So during the projectile motion, the total energy of the projectile motion is conserved at all points of its motion. So this is one more important point we got it here. Total energy of a projectile is conserved. Conserved means remains constant, remains the same. Conserved means remains the same throughout the projectile motion. Throughout the projectile motion. So from this problem we understand three important rememberable points because of the projectile motion. The first point at here is during the projectile motion, in projectile motion, potential energy is maximum at its highest point, and at highest point kinetic energy is minimum, and throughout the projectile motion the total energy remains constant. The total energy is conserved during the projectile motion, remains constant. So that's the 3 points we got it from this problem.